Welcome to Module 3.15, where we'll explore the interpretation of statistical results in healthcare research. Moving beyond merely calculating statistics, this module focuses on understanding what results actually mean in practical terms. We'll examine the distinction between statistical and practical significance, various measures of effect size, and common misinterpretations that can lead to flawed conclusions. This knowledge is essential for translating statistical findings into meaningful healthcare applications. A critical distinction exists between statistical significance and practical importance. P-values indicate only whether results likely occurred by chance, not their magnitude or importance. Effect sizes provide information about the strength of relationships, which may be statistically significant but too small to matter clinically. Clinical importance depends on context. Even small effects may be meaningful for serious outcomes, while larger effects might be irrelevant for minor conditions. Confidence intervals provide valuable information about precision and effect magnitude that p-values alone cannot convey. Sample size heavily influences statistical significance. Large samples can make trivial effects significant, while important effects may be non-significant in small samples. Multiple testing increases the risk of false positives, requiring adjustments like Bonferroni corrections. Thoughtful interpretation considers both statistical properties and real-world healthcare implications. Effect size measures quantify the magnitude of relationships in standardized ways that facilitate interpretation. Cohen's D expresses differences between groups in standard deviation units, with values around 0.2, 0.5, and 0.8 conventionally considered small, medium, and large effects, respectively. Odds ratios, common in case control studies, indicate how odds of outcomes compare between groups. Risk ratios, preferred in cohort studies, directly compare probabilities of outcomes. Correlation coefficients quantify relationships between continuous variables ranging from -1 to +1. Number needed to treat, NNT, has particular clinical relevance, indicating how many patients must receive an intervention to prevent one adverse outcome. These measures complement significance testing by answering not just whether an effect exists, but whether it matters enough to influence healthcare decisions. The common misinterpretations undermine the perhaps most fundamental is confusing correlation with causation. Statistical associations do not necessarily indicate causal relationships. P-value misconceptions abound, including treating p less than 0.05 as proof of effects, or p greater than 0.05 as proof of no effect. Over-interpreting small effects while ignoring their practical relevance can lead to implementing ineffective interventions. Focusing solely on point estimates while ignoring confidence intervals overlooks uncertainty in findings. Statistical tests rely on assumptions about data distribution, independence, and measurement. Violation of these assumptions can invalidate conclusions. Critical consumers of healthcare research recognize these potential pitfalls, enabling them to distinguish meaningful findings from statistical artifacts and apply evidence appropriately in clinical practice.